In this task, we will continue with the visualization and in this task, we will visualize the relationship between the geospatial attributes, that is longitude and latitude, with the median house price. We have the data set and the information of the data is df.info open and close bracket, and it's a pandas df is pandas data frame with 20,640 entries. In the data columns there are 10 columns with longitude, latitude, housing, median age, total rooms, total bedrooms, population, households, median income, median house value, ocean proximity. Ocean proximity is of category type, and the rest of the variables are of float 64. And the memory usage is more than 1.6 megabytes. We create geometry from the given longitude and latitude, project the geometry with reference to the coordinate reference system, and visualize the median house value. So let's make a copy of the pandas data frame. So we make a copy of the original data set. Let df gpd equal df.copy open and close bracket. Let's print the first few lines of this copied data frame, and this is how it looks like. Now to create the geopandas, we need to import geopandas library as gpd. Create a geometry column from the given longitude and latitude. Let geometry equal gpd.points underscore from underscore xy bracket x equal longitude, comma y equal latitude. We could say over here, what we can do is we can attach df df gpd it's not working. Okay. Okay, so we could also say df instead of df we will use df gpd, because we don't want we want to work with df gpd. Let's run this. So we get this. Let's copy this again and let's run this. Match the data frame with the geometry column. So let df gpd equal gpd dot geodata frame of df gpd, comma geometry equal geometry, the geometry that we found, comma crs equal epsg colon 26946. Now what we're doing over here is we are merging the data frame df gpd with the geometric column, and this CRS, this is the coordinate system, and we set to the coordinate system of California. Let's look at the first few lines. df gpd dot head open and close bracket prints this, and then there is a geometry column listed at the very end, and we can see that the geometry column contains points. It's not multi-polygon or polygon, it's point, so it's just the dot. Okay, so we have already done, we have checked the first few lines. So let's check the data information. So dfgpd.info open and close bracket. So we get a geodata frame, geopandas geodata frame, and the number of rows is 20,640, and the data columns, there are 11 columns. We have added geometry column as of data type geometry right in the end, and the memory usage is more than 1.7 megabytes. This data frame has 20,640 data rows with 11 columns. With 11 columns, containing 9 float 64, 1 object and 1 geometry. Memory usage is 1.7, more than 1.7 megabytes. We could further change the object type to category type. Next, we will check the coordinate reference system and visualize on a static plot. Transform the column ocean proximity to category type. So dfgpd.ocean proximity equal dfgpd.ocean proximity.s type of category. Check data information, dfgpd.info open and close bracket. So we get so we can see that the ocean proximity, the data type is now category. Let's check the values in the ocean proximity. Let's insert a new row, new cell above, and dfgpd dot ocean proximity dot unit. We have 5 categories: nearby, less than 1H, ocean, inland, near ocean, island. Check the coordinate reference system of the geospatial data frame. gpd.crs gives projected so we have we have converted this to EPSG 26946, and the info, and then and then we want CRS, coordinate reference system. So that gives this. Now projected CRS EPSG is 26946. Name is NID 83 / California zone 6. Axis info is Cartesian. X is easting meter. Y is north, northing meter. Area of use, name is United States. California, county is Imperial. Orange, Riverside, San Diego. Bounds is -118.15, 32.53, -114.42, 34.08. Coordinate operation. Name is SPC S83 California Zone 6 meters. Method is Lambert conic conformal. Datum is North America, datum 1983. Ellipsoid GRS 1980. Prime meridian Greenwich. Import matplot live.pyplot has PLT. So we will do the static plot first. Plot the geopandas data frame. So this is a static plot that we are plotting. df dot plot bracket column equal median house value, comma cmap equal blues, comma fixed size equal 15, 15. So the height is 15 and the width is 15. Legend equal true, legend underscore kwds equal. So this is we are forming a dictionary of the values. So label is median house value, orientation is horizontal. So this will create the legend, horizontal legend, and it will show median house value. plt.title, in the bracket we will put relationship between the geospatial attributes, that is longitude and latitude, with the median house value in 1990 California data. plt.y label is latitude, plt.x label is longitude, plt.show open and close bracket. So we get this. So the darker blue values show, the scale is ranging from 0 to 500,000. And in the dark blue and the blue color, the mapping is from light blue to dark blue. So the dark blue is more towards 500,000. So we can see that along the coastline, the houses are of value, of higher value. And for the inland, the houses are of lower value. Except one or two houses, we can see that these two houses here, they are of high value. The dark blue colored locations are for location of houses with median house value of at least 500,000. The median house value decreases as the blue colors become lighter. There are higher median house value located in the ocean, and there are some in inland as well, but mostly are located along the coastline. So we can see one or two houses located on the island which are of very high value as well. Now we will show the geospatial plot. So we will import Folium. From Folium.plugins, import heat map. Create a base map. Let m equal Folium.map of location equal 37.7749, which is latitude, and longitude is minus 122.4194, and that's in the square bracket, comma zoom underscore start equals 6, and printing m gives us this, and this is for the region California. So we can see Sacramento, California, San Jose, Nevada, Salt Lake City, Tucson, Phoenix, Mexico, Las Vegas is here, Los Angeles, and yeah, so Okay, so let data equal list of zip bracket geometry dot y. So the y value of the geometry, comma geometry dot x. So that will be the x value of the point geometry, comma and median house value. And close the brackets. And printing data gives us this. So we have, for example, this one over here. We have the latitude 37.85, the longitude minus 122.26, and the median house value of 261,100. Okay, let's create a heat map to visualize the density of house values across locations. Let heat map equal heat map bracket data equal data, so the data that we listed here, comma radius equal 15, comma gradient equal 0.2 colon blue, comma 1 colon red, and then dot add to add underscore 2 to bracket m, and we print m. So we have the heat map like this. So what if we reduce the radius to say 7? So when we reduce the radius to 7, it becomes a bit lighter. And let's keep it to say 20. Let's do 20. But it does. It's very dark. So let's do say 10. So 0.2, it ranges from blue to red. Red ones show um, the median house values, which are very lot of houses, and the light blue shows there are less houses. Add markers with basic information for clarity. For ocean house value geometry in DFGPD, and then we this double square bracket creates the data frame subset of the big data frame, and it takes only ocean proximity, median house value, and geometry, and it dot values. So we look at the values and we assign it to the three values. Ocean proximity is we take it as ocean, median house values we take it as house value, and geometry we take it as geometry. So let latitude equal geometry dot centroid dot y, and let longitude equal geometry dot centroid dot x. Let marker equal folium dot secant marker, open bracket, location equal bracket latitude comma longitude, close the bracket, comma radius equal 3, adjust radius for visibility. Let pop-up equal f and then printing house value colon the dollar sign, and then the curly braces house value, the house value, this house value which is the median house value, comma colon, and then comma, and then 0.0f. So so when we click on a bubble here, then we see that this is how it is printed. So house value, colon, so this part over here, house value column, and then dollar sign, we want a dollar sign, and in bracket it's the house value 79,200. So 0.0f, 0.0, it shows that there is no decimal space, so it's a rounded house value. And the color equal gray, so the dots are of color gray, and radius equal 3. The radius of these dots are 3. And fill underscore color equal gray, so the circles are filled with gray color. Fill underscore opacity equals 0.7, and then add dot, close the bracket, dot, add underscore to bracket m. Now if I change this to point, say 5, then I expect the decimal numbers to be, there should be 5 decimal numbers. Let's run that. And let's have a look. It's still running. Let's wait for that. It takes a bit of time. So now while we are waiting for that, we will display the map with legend for the heat map. So to display the map with legend for the heat map, we'll pass the command m dot add underscore child of heat map. So m, printing m, that gives us this. Now still waiting on that. So still doing it. And then when we if we run all the commands in one cell, we get this. The map looks like this. So to make it bigger, we scroll out, and if we click on the bubbles, this should give us the house value 54,300. And along the coastline, the houses are of high value. Okay, so the median house value of less than 500,000, less than 50,000 are mostly located in inland California, and is shown on the interactive map using blue circle markers. So no, not blue. Um, not blue. So we haven't marked the less than 50,000 with blue circle markers. So this is we need to correct this. We notice at least 3 median house value located near ocean is less than 50,000. So yeah, so if you make changes to this marker and include the house values which are less than 50,000 and show it using blue color, then it will show you at least three houses of value less than 50,000 located near ocean. The median house value of more than 500,000 are mostly located near ocean. We notice that the median house value of more than 500,000 is located in inland, which may be an outlier. Okay, so now if you want to see where was that? Oh yes, so 0.5, coming back to 0.5f, now we have the graph here. So let's click on one of the bubbles here. So you see that there is 5 decimal places. We don't want that 5 decimal place. We only want 0. We don't want any decimal numbers. So we will put 0 here. Okay, now if I want the house value, say let's delete this. Okay, now if I want to see 50,000, so say houses less than 50,000, so I will do DFGPT. First I will subset median house value so DFGPD DF underscore GPD of median house value less than 50,000, and then close the bracket. That will subset the DFGPD with the median house value less than 50,000, and then I will choose ocean proximity, median house value and geometry values, and then I will plot it. So if I do that for only a median house value less than 50,000 and I run it, I guess this will take this takes less time. So all these values here shows for median house value less than 50,000. So for example, if I click on one bubble here, that house is 44,000, 400. And if I want to only plot for more than 500,000, more than or equal to 500,000, then yeah, so I can see that those data, those bubbles, these bubbles all represent the house values more than or equal to 500,000. If I click on one of the bubbles, this house is of 500,001. So thank you.